Okay, welcome back to Real Analysis. Continuing to look at theorems from calculus about the derivatives, section 7.6. First one we're going to look at is called Rolle's theorem. It's probably a familiar statement to you. This Rolle's theorem comes from the first subsection of section 7.6, so 7.6.1. Keep this kind of short and focused in this video. I'm going to state the theorem, look at a proof of it, do a couple of examples, and that'll be the video. All right. So what does the theorem say? Well, it's about a function on a closed interval. So the preamble, take a couple of numbers, a and b, assume a is less than b. We got a function defined on that interval, closed interval from a to b. What are the hypotheses? The important part to focus on in about this function, that it's continuous and it's on the entire interval, and we're going to assume it's differentiable on the open interval. Okay, so we won't say anything about the differentiability at the endpoints. The endpoints aren't interior, and our notion of derivative kind of requires an interior point on an interval. So that's our hypothesis. I've got this function on a closed interval. It's continuous on the whole thing, differentiable on the open interval. One more set of hypotheses, and you can see it in the picture down there. We're going to assume that the value of the function is the same at both endpoints. So if that's true, if the value of the function is equal at a and b, f of a is equal to f of b, then there has to be some value in between, some c in the interior of the interval where the derivative vanishes. F prime of c is equal to 0. Okay, so you can see it in the illustration that I took from the text here, that I've got this function f. It looks like in this picture f is defined on a larger domain, but in particular it's defined on the closed interval from a to b. Okay, it looks continuous and differentiable from those visual characteristics. And the important part of the hypothesis is that the function's value at the two endpoints is the same. Okay, so that f of b and f of a have the same value. And the theorem is saying that there has to be some place where the derivative vanishes. In fact, in this picture, it looks like there's two such places. So Rolle's theorem doesn't forbid the derivative from being 0 in more than one value. It just says that it has to happen at least once. Okay, so this is probably a familiar statement from calculus. Let's go ahead and just check out the proof. So I'll use the theorem as usual to kind of state the notation. I won't re-quantify everything, but I've got this continuous function on a closed interval, differentiable on the open interval. And I'm going to kind of start the proof by saying, like, well, maybe that function is a constant. So maybe not only f of a is equal to f of b, maybe f only takes on one value. Well, if that function is a constant, then its derivative is identically 0. Yeah, the derivative of a constant function is identically 0. So you could just take c to be any value in a to b you want. There's infinitely many values of c in there that would satisfy it. Okay, so we've kind of done away with that case. So I'm going to be assuming from now on that f is not a constant. It's not a constant function. So I'm going to invoke our extreme value theorem, our theorem from chapter 5, 5.50. The extreme value theorem says that, f achieves both an absolute minimum value, which I'm calling little m, and an absolute maximum value, which I'm calling capital M. Okay, so there's inputs that actually equal those things. F of something is little m, f of something is capital M. That's what the extreme value theorem says. That's by the continuity of f on this closed interval. But we're assuming that f is not a constant function. So this is a little bit of a subtle point. Maybe you want to stop the video and think about this. At least one of those values, I mean little m or capital M, cannot equal the common value at the endpoints. Okay, f of a and f of b. Maybe you should stop the video and think about why that's true. So dramatic pause. I'm just going to say it right now. If both little m and capital M equaled f of a and f of b, well, that would mean that the absolute minimum value and the absolute maximum value of the function were the same. Well, the only such function that can do that is a constant function. Yeah, a function that takes on at least two values cannot have the property that its minimum and maximum are the same. Okay, so at least one of capital M or little m has to differ from f of a and f of b. So without loss of generality, I'm going to say that capital M isn't f of a. You can rewrite this proof if you want, assuming that little m isn't. It'll go through the same way. Okay, so if capital M isn't f of a, then it's actually strictly bigger than it. Because remember, capital M is an absolute maximum. It's an absolute maximum value. Okay, so the extreme value theorem says that there's some point in our interval that achieves that maximum. There's some C that equals M. And in fact, C can't be A or B because we just said that we're assuming that M, that is f of C, is bigger than f of A. F of A is equal to f of B. So this C is actually an interior point. So I made a big deal about that. I made a big deal about C being an interior point because it's an absolute and hence local maximum. We're assuming that F is differentiable on the interior, so F prime of C exists. So our theorem last time, not our book, but remember the calculus book I showed you called it Fermat's theorem, it's theorem 7.18, says that the derivative has to vanish. The derivative has to equal 0 at an interior local extremum. And this global extremum is certainly local. Cool. So that's the proof of Rolle's theorem. Nice. So you can stop this video and kind of take your own notes at your own pace and make sure that every step in that argument is digestible. Just going to look at a couple of examples. If I define a function f on, say, the interval from 0 to 1 over pi, we've looked at this example. It's this x times sine of 1 over x for non-zero x and 0 at x equals 0. We've looked at this example, or we looked at one like it, x squared. You can stop the video, and it's good practice to recapitulate these details, that function is continuous on that closed interval, and it's differentiable on the open interval. From 0 to 1 over pi, and you can check the math that the value at the two endpoints are 0. F of 0 is 0, f of 1 by definition, and f of 1 over pi is also 0 because it's equal to 1 over pi times the sine of pi, which is 0. Right? And I'm just going to scroll down and kind of show you a picture of this function as we're talking about it. That's the graph of this function, f of x. Didn't label my picture. So it's x times sine of 1 over x. It's this dampened, oscillating, like crazy trig function. If x isn't 0, and then its value at 0 is equal to 0, right? So you can kind of see in the picture that it's continuous. It's differentiable on the open interval. If x isn't 0, then you can differentiate that formula using the usual rules. Again, I'm assuming the differentiability of the sine function, the product and chain rule, and so on. So it's differentiable on the open interval. You can check by definition that this function is not differentiable at x equals 0. All right, so unlike the example x squared times sine of 1 over x we looked at, I'm going to leave this detail to you, but it's not differentiable at x equals 0, but it still satisfies the hypothesis of Rolle's theorem, because Rolle's theorem doesn't insist that it be differentiable at the endpoints. They're not interior points. And you can see in this picture that there's actually infinitely many values of C in this interval where the derivative is 0. I'm just going to kind of highlight some of them, but the derivative of this function would be 0 right there. It would be 0 again right here. It would be 0 right there. So there's infinitely many values. It's a nice challenge to try to say exactly where they're occurring. So I'll leave that challenge to you. But I'm just saying visually by this picture that, I said above, Rolle's theorem doesn't say that there's going to be exactly one place. In this particular example, it looks like there's lots of them, infinitely many values of C, where f prime of C is equal to 0. Okay, so let's look at one more example before my voice goes out completely here. This seems like a little bit out of a hat, but I wanted just to do something that kind of illustrates, what somebody could do with some result like Rolle's theorem. So suppose I write down some cubic equation, x cubed plus x squared minus 1, and I want to try to convince you that that equation has exactly one solution in the closed interval from 0 to 2. Okay, so that's the statement of the example. I'm going to convince you that that equation has a solution in that interval, and that there's exactly one of them. Okay, so just to sort of fit into our theory, let me define a function on the closed interval by that cubic expression. Okay, it's a polynomial function, so it's continuous and differentiable everywhere, in particular for all x on the interval from 0 to 2. F is defined on an interval bigger than 0 to 2. It's defined on the whole real line. So that's what I'm talking about, differentiability at the endpoints. But we don't have to worry about that right now. Okay. So then I'm just going to check out the value. I'll let you check the arithmetic, but I claim that F is negative at 0 and it's positive at 2. So you can stop the video and verify that. So the intermediate value theorem says that it's 0 somewhere in between. All right. So that means I've got at least one solution. There's at least one number between 0 and 2 that makes that expression equal to 0. That's from the intermediate value theorem. Cool. Well, how do we rule out the fact that there aren't any others? Well, suppose that there's actually two numbers. I'm going to call them A and B. Suppose that they're in that interval from 0 to 2. They couldn't be the endpoints because we've already said f of 0 is -1 and f of 2 is 11. Let's, without loss of generality, assume A is less than B, and suppose that they both are solutions to the equation. That is, that f of A and f of B would both be 0. Okay, well then we've met all the hypotheses of Rolle's theorem. I've got a continuous on the closed interval, differentiable on the open interval function, whose values at the endpoints are both 0, so they're equal to each other. So Rolle's theorem would say that the derivative is 0 somewhere in between A and B. Some number between 0 and 2 would make the derivative 0. But the derivative of this cubic polynomial is 3x squared plus 2x by our differentiation rules. And if I kind of factor that thing, I can see that the product of x and 3x plus 2 is never going to be negative if x is at least 0. If x is at least 0, 3x plus 2 is at least 2. The product of two positive numbers is positive. Okay? So it can't be the case that there's some d between 0 and 2 that makes this derivative 0. The derivative is never 0 between 0 and 2. Okay, so what does that mean? It means that the c that we found above is the only solution to that equation. That cubic equation has exactly one solution. Okay, thanks for listening.